Before we actually get to talking about probability mass functions, let's lay some foundation and talk about functions in general. For instance, let's think about this graph here, which is the graph of the function f of x equals x minus 1. We want to think about functions as inputs and outputs, and what they tell us is that for any value we input for x on the right-hand side here, the function will return to us a value for this left-hand side, this f of x value. So for instance, if we pick x equals 1, then the function gives back to us 1 minus 1 or 0, which means if we set up down here a table of inputs and outputs, so we'll have our inputs x and our outputs f of x. We said that if we pick an input of x equals 1, our output is 1 minus 1 or 0. If we pick an input of x equals 2, we get 2 minus 1 or 1. So an input of 2 gives an output of 1. An input of 3 would give an output of 2, etc. And of course that makes sense because this function here is just telling us whatever value we put in for x, we're going to subtract 1 from it to get the output. And so we can see that all of the outputs are 1 less than the input values. And we can see that in the graph as well. Obviously all of these then become coordinate points. So we have this coordinate point 1, 0, and we see that right here. We also have this coordinate point 2, 1. We see that point here at 2, 1. We see that it's along this line. And we have the point 3, 2. So we go out to x equals 3 and up to 2, and we sketch in that point. So what this function is saying is that if we pick a value x equals 2, we come up to the graph of the function, and then we move straight over to the vertical axis, and we see that the value we get back is 1. So when we pick 2, we get back a value of 1. Or if we pick 3, we come up to the function at x equals 3, and then from here we go over to the vertical axis and we find 2. So if the input is 3, the output must be 2. If the input is 2, the output must be 1. If the input is 1 here, the output must be 0. So 0 and 1. So we can get these input-output pairs just from the function, as we showed with our table here, without ever having the graph. We can also get the input-output pairs from the graph itself, and the input-output pairs from the graph will always match the values we get in our table, the values that are generated when we plug in values of x to our function. Well, a probability mass function works the same way, except that we plug in values that the variable can take on, and what's returned to us is a probability. So here, in this scenario, what was returned to us was a value along the vertical axis here, a value for f of x. In a probability mass function, what we get back is a probability that that input value occurs. So as an example, let's look at this probability mass function. This function models the probability of flipping heads if we flip a coin 2 times. Now, we've already looked at probability with coin flips, so we know that when we flip a coin 2 times, we can flip heads and then heads, we can flip heads and then tails, or we can flip tails and then heads, or tails and then tails. There are 4 possible equally likely outcomes when we flip a coin 2 times. Now, if we think about the number of heads we can get over the course of 2 coin flips, we can either get 2 heads here, which we see in this outcome. We can flip heads once, or 0 times. So the only possible options are flipping heads 0 times, 1 time, or 2 times, and that's what we see here in the probability mass function. X can be 0, it can be 1, or it can be 2. So this part of the function here represents all of the possible outcomes of our discrete random variable. Now, it's important that we say discrete random variable because we're only going to use probability mass functions to model discrete random variables, not continuous random variables. And the reason is because we have to be able to identify a specific probability for each outcome. And remember, with continuous random variables, we can continue to measure an infinite number of in-between values. So whereas in this example, where we can flip heads 0 times, 1 time, or 2 times, if we had a continuous random variable, we might need to look at the probability of 0 times, but then also a quarter of a flip, or a half of a flip, or 0.4782935 flips. Every value an infinite number of values in between 0 and 1, and an infinite number of values between 0 and 2. And we can't define a specific probability for all of those infinite number of values. So we only use probability mass functions to model discrete random variables where we have this countable set of discrete values that our random variable can take on. So we have to have a discrete random variable, and all of the values that we can get are defined over here in this part of the function. This part of the function gives the probability that each of these outcomes occur. So this part here is p of x, the probability that the specific value of x occurs. And we can see here with our little chart we made that of the 4 equally likely outcomes, we'll flip heads 0 times, exactly 1 out of those 4 outcomes. So there's a 1 in 4 chance that we'll flip heads 0 times when we flip a coin 2 times. And so a 1 in 4 chance is a 0.25 chance. The same thing happens here. The probability of flipping heads 2 times happens only 1 out of these 4 possible scenarios. So that probability is also 1/4 or 0.25. But the probability of flipping heads exactly once happens 2 out of 4 times. So the probability of x equals 1 is 2/4 or 1/2 or 0.5, 0.5. So we've matched up each of these probabilities with the corresponding outcome. It's important to say now too, that another requirement of a probability mass function is that all of these p of x values here have to add to 1, because remember, total probability is always 1 or 100%. Every individual probability value has to fall between 0 and 1. So 0.25, 0.5, and 0.25 all fall between 0 and 1, and these values add up to 1. 0.25 plus 0.5 plus 0.25 is 1. So we have the requirement that these values add to 1. We have the requirement that we're dealing with a discrete random variable. And we just said it a little bit, but let's be a little bit more explicit, that all of these p of x values have to be positive. So we can contrast that with this kind of function, which we might have learned about in an algebra course. In this kind of function, we can find negative values of f of x. For instance, if we were to set x equal to 1/2, our input would be 1/2 and our output would be 1/2 minus 1 or negative 1/2. And we see that along the graph here. If we pick this x equals 1/2 value and we connect it to our graph and then go straight over to the vertical axis, we see that we get a negative value of 1/2. And f of x, this function, is perfectly defined for that set of values. We could say the input is 1/2, the output is negative 1/2. That's totally valid. That satisfies this function f of x. But for probability mass functions, we can never find a negative output like this. In our case, that means we can never get a negative probability. So all of these values right here have to be 0 or positive. They cannot be negative, which makes sense because negative probability is really nonsensical. So those are our 3 requirements. We have to be dealing with a discrete random variable, which means we have a countable set of values. Our set of values is not continuous. We don't have a continuous random variable. And all of these probability outputs here have to be defined between 0 and 1, and in total, they have to add to 1. By definition, of course, that means they can't be negative. So with that said, the only other thing we want to say about probability mass functions is that sometimes we'll see them written this way, and then sometimes we'll add an extra line to the function, or we'll see this line added to the function that says that the function is 0 for any other values, or 0 otherwise. And if we have this line, all it's doing is clarifying for us that the probability that x takes on any other value other than 0, 1, or 2 is 0. It doesn't really change anything because our probabilities still add to 1. We're just explicitly stating by putting in this extra piece of information that these are indeed the only values that x can take, and confirms for us that the total probability of this probability mass function is defined in these first 3 rows here. So sometimes we'll see this, sometimes we won't. We don't necessarily have to have it. It's just important that we meet all of the other requirements of discrete random variable probabilities defined between 0 and 1 that all sum to 1. Now, just like with this function, this algebraic function, where we were able to sketch its graph, let's talk about the graph of a probability mass function. So really, we're setting it up on horizontal and vertical axes just like we did over here. And we always include all possible values of x, our discrete random variable, along the horizontal axis. So here, our possible values for x were 0, 1, or 2, so we include those along the horizontal axis 0, 1, and 2. And then along the vertical axis, we'll mark off increments of our probability p of x. And then in order to graph this probability mass function, all we do is add in these columns here, which show that the probability that x is 0 is 0.25, or 25%, or 1 in 4. So we draw in this bar, this line, at x equals 0 and extending up to 0.25, whereas the probability that x equals 1 is 0.5. So at x equals 1, we sketch in this bar extending up to 0.5 along the vertical axis. And then again here at x equals 2, since the probability associated with x equals 2 is 0.25, we sketch in this bar all the way up to 0.25. So seeing the way that these two things match each other, we should be able to, from this function, sketch the graph of the probability mass function. But we should also be able to take this graph and define in algebraic form up here the probability mass function f of x. Obviously, if we were starting from the graph, we could start here along the horizontal axis to see that x is defined at 0, 1, or 2, and we could set up this part of our probability mass function. And then for each of those values, 0, 1, and 2, we would find the corresponding probability and we would set up these pieces. And then we would just say f of x is equal to, we'd have our open brace here, and then our 3 scenarios defining the probability for each possible value of the discrete random variable. So we should be able to move back and forth between this algebraic representation and this visual graphical representation. And then the only other thing we want to say is that just like when we talked about probability before, and we learned about complementary probability and or probability, we can answer those same kinds of questions with a probability mass function. So whether we have this representation of f of x or this graphical representation of f of x, we should of course be able to state the probability that x is equal to 0 or x is equal to 1 or x is equal to 2. But we should also be able to find the probability, let's say, that x is equal to 0 or 1. We know from the addition rule that the probability that x is equal to 0 or 1 has to be 0.25 plus 0.5. So the probability that x is 0 or 1 would be equal to 0.25 plus 0.5 or 0.75. Or we could say something like, what's the probability that x is not 1? So the probability that x is not 1, well, that would be everything but this 0.5 here. So we would take 0.25 plus 0.25, and we would get 0.5. Or the probability of not 1, we could calculate as 1 minus the probability of x equal to 1, or 0.5, and we get the same answer, 0.5. And of course, we could answer these kinds of questions from this representation of f of x, but also from the graphical representation of f of x. For instance, this probability of 0 or 1 question, we would just identify here the probability as 0.25, and here the probability as 0.5. We would add those together to get 0.75. So that's the idea of a probability mass function, how they're related to the original idea of a function as a set of inputs and outputs, how the outputs are defined as measures of probability, how we can only use them for discrete random variables, where the probabilities are all defined between 0 and 1 and sum to 1, and how we can represent probability mass functions both algebraically and graphically, and use both representations to answer all different kinds of probability questions.